Let's start out by giving this 18-term summation a name. Let's call it S for sum. Imaginative, huh? Now, how do we know it has 18 terms? Well, notice this very first number 1 is the same thing as 2 times 1 minus 1, which is a form for an odd number, right? Now, right here, this would be 2 times, what, 18? 2 times 18 minus 1. Okay, so there's definitely 18 terms in this expression, and also each of the, let's see, what do we have here? 2 times 8, 18 terms. Now, each of the terms are of the form 2i minus 1 times 2i. There's an even number in the middle of each of the terms. And then parenthetically 2i plus 1. Now, this symmetric way of representing this thing ends up being quite useful computationally. And again, y'all, there are 18 terms, starting at 1, 18 right here. Each of the terms begin with an odd number. And you can see kind of this, the 3, it ends here, and it starts here, 5 ends here, 5 starts here. And that would continue on. Now let's rewrite this in summation notation. All right. Now, again, this is evident from the very beginning. It's conceivable to write this is 2i, the sum end is 2i plus 1. This wouldn't be wrong. This would be an approach, but see if you can think about why that would be flawed. Or not, flaw is probably not the right word, but multiplying all of this out, this would be consecutive numbers in that form, starting with an odd number, right? 2i plus 3. But the drawback to this is that when you expand it out, you don't get something as nice as the symmetric representation. When you multiply all of this out, you get a very simple binomial 8i cubed minus 2i. If you expanded this out, you would have what, I squared terms probably, I guess, right? So this is definitely the choice, this so-called symmetric choice right here. Okay, now at this point, folks, you probably recognize there are formulas, closed form formulas for the sum of the first n cubes and sum of the first in integers. All right, and so that's what I used right here. These are the two results. The sum of the first n cubes is given by this, and the sum of the first n integers is given by this. Okay, so we actually just used that right down here where n is equal to 18, clearly. Okay, n is equal to 18. And again, there's an 8 in front of this, which would just be a constant that would come outside of the summation. So that's where this 8 comes from. And of course, right here, 2. And we have 2 right here, right? Okay. So the rest of this, as you can see, is just substituting right here. We substituted into this formula for n equals 18. And then right here, we substituted into this formula for n equals 18. All right, y'all. And here's all the arithmetic, and all 18 of those numbers add up to something a little bit shy of 250,000. Okay, so not a bad problem. It was useful just to express it this way, just because, again, because of the symmetry. If you had expressed it like this, that you would have had cubic terms, squared terms, linear terms, and a constant term, all of which could be done because there's a formula for the sum of the first n squares. But this symmetric approach right here is clearly the right approach in terms of minimizing the computations. And that's all for tonight. Hope you enjoyed.